So next we have Vinod Mamale. He's going to be telling us about effect of fluctuations on symmetry and fields.
So today I will be talking about effect of fluctuations on symmetry and fields. So which symmetry and which fields we will see. So any physical system is not ideal. So there will be some fluctuations in it. That the type of fluctuation can be thermal fluctuation, quantum fluctuation, or mechanical fluctuations, or any other type of fluctuations. So these fluctuations can lead to many interesting effects such as spontaneous breaking of symmetry, Casimir effect, or other kind of effects. So every time when there are in physical system, we usually have the competition between extremization of action or energy. So system tries to minimize the energy as well as tries to increase the entropy. So there will be competition between that. So today I will be talking about three such effects. One is thermal fluctuation, which lead to realization of Z symmetry, and this in turn changes the nature of confinement deconfinement transition. The other thing is effect of thermal fluctuations on uh, mechanism of topological defect formation, and the third thing is mechanical effect of mechanical fluctuations, such that gravitational waves drive the parametric resonance in non-abelian gauge fields. So first one, the thermal due to thermal fluctuations, realization of Z symmetry, and nature of confinement deconfinement transition. So at finite temperature, bosonic and fermionic matter fields satisfying only periodic and antiperiodic boundary conditions contribute to the partition function. So this breaks the Z symmetry of the action. So here we are considering only SU3 Higgs, so it breaks the Z3 symmetry of the action. So we are considering SU3 Higgs in fundamental representation, and we study it near the CD transition temperature. So the partition function function has two parts. One is one which has the Z symmetry, and other one which breaks the Z symmetry. So the pure gauge part, as well as uh, Higgs, other than Higgs gauge interaction term, other terms have the Z symmetry. Only the Higgs gauge interaction term breaks the Z symmetry. So we work with this lattice version of this, and we do this in Higgs symmetric phase, because in Higgs broken phase the Z symmetry is explicitly broken. So in principle, when one integrates out the matter fields and the special gauge fields, one would expect that partition function can be written in terms of Polyakov loop, which is the order parameter of CD transition, and there will be uh, action will action will act as a Boltzmann weight, and there will be density of state. So this G of L, it is Z3 symmetric, as well as it depends on n tau, and n tau is number of uh, time time steps. So it increases with n tau. So at fixed temperature, higher n tau corresponds to approaching continuum limit. So this higher n tau leads to higher GL, and so we will see that density of state dominates the compared to Boltzmann weight. Then density of state will dominate, and we will see the restoration of Z3 symmetry, which was broken even in the action. So that's how the Z3 symmetry is realized in the continuum limit. So here we have two plots of at n tau equals 2 and n tau equals 4. So we see that for n tau equals 2 we have expectation thermal average of Polyakov loop, and we see that the nature of transition is crossover, whereas when we go to n tau equals 4, we see that it changes to the first order phase transition, and that as n tau equals 2, we have limited GL will be small for n tau equals 2 and GL will be larger for n tau equals 4. So that is the effect of density of states. So to verify this, we have also done comparative studies to see that it's actually the effect of density of state. We have done comparative studies with Z2 Higgs, as well as we have done uh, analytical calculation of one-dimensional chain with the SB part of the action, and that was done for general SUN as well as for Higgs. So we have verified that in both the cases we have verified that density of state is the responsible for this restoration of Zn symmetry. So the second problem we are talking about is effect of thermal fluctuations on the mechanism of topological defect formation. So Kibble-Zurich mechanism is used to give a theoretical description of topological defect formation. So it has two postulates. One is that there are formation of domains, and the second one is that geodesic rule. So formation of domains says that there will be the order parameter will be uniform in regions. So these represent different domains. So order parameter will be uniform in this, and when here we are considering order parameter space to be circle, and when it winds non-trivially, we will get a topological defect which is at the collision of the different domains. So like these are topological defects will be formed there. So that is the first postulate, and the second postulate is geodesic rule, which says that from here to here, when order parameter traverses from here to here, then because it should change slowly, otherwise the gradient of field will contribute to the energy. So it will cost larger energy when it traverses longer path. So example here we have, if we consider these two domains, we have considered the possibility of how the order parameter changes from in between those two. So it is possible that it changes like this, which is which leads to minimum energy, and so it is the geodesic path, and the other one is it takes longer path, and also there will be other possibilities other than these two also, where the order parameter winds around and gives non-trivial topology, but so all of these possibilities are there. So now so there are like competition between, like, as one decreases the temperature, the fluctuations will decrease, but at the same time the correlation length increases as one approaches critical temperature, and as one is approaching from above, that whether the fluctuation will decrease faster or whether the domain size will be getting larger. So what happens to the geodesic rule? So we see that most of the time geodesic rule is violated, and it depends on what is your quench rate and where the system gets frozen. So this is the defect density, and it's found, according to Kibble mechanism, is proportional to Xi correlation length when the system freezes out. So we see that we have done for 2dxy model and 3dxy model, we see that number of defects are like simulation estimates that it will be very larger compared to the Kibble-Zurich mechanism estimate. Same for 3dxy as well as 5-4 theory, which we have studied. So this is because we see that geodesic rule is violated very by very much large percentage, and so fluctuation result in higher number of the defects in both of the 2D XY model and 3D XY model. So the third thing is that we consider fluctuations, periodic fluctuations in space-time, which lead to parametric resonance. So it was previously seen that space-time oscillation generate parametric resonance in matter fields. So we wanted to study what will be the effect of such fluctuations on non-abelian gauge fields. So we have considered small periodic space-time fluctuation on top of Minkowski background. So why this particular background is considered? Because this mimics the plus polarized gravitational wave traveling in the z direction. So this leads to this equation of motion for non-abelian gauge field, and we can see that when we go to the linear approximation, this is same as Maxwell's equation with the in this metric background. So we analyze these equations for and evolve those equations, and we studied the different modes of those fields. And in linear approximation, we find that these are the equations for those modes of those fields, and these are for A1 and A2 and A3. So these clearly have f of t, which is also a periodic function of periodic function in time. So we see that these equations are give rise to parametric resonance. So these fields will show a very large increase, and so this results in increase in energy density also. So this plot is here is energy density versus time, and this energy density non-abelian versus abelian. So we have plotted the difference only, and we see that as time goes on, the difference goes on increasing. So as we can see, this is log plot, and even the slope of this thing changes. So it's like a very strong increase in the energy density. So we see that non-abelian have more increase in energy density compared to abelian gauge fields due to parametric resonance. So another thing is we want to study the CP violating term E bar dot B bar, how it will evolve due to parametric resonance. So we see that E bar dot B bar in linear approximation results to this condition, and even if you look at this condition, it depends on A3 dot by A3, which when one looks at this equation, these two are different equations, as A3 is coupled to A0, as well as there is some extra term of rigid. So even if at t equals to 0, if this equation is satisfied, it won't be satisfied at later times. So we study when FF dual term in like non-abelian, we consider FF dual term, and we see that parametric resonance leads to larger values at later times, as shown in the figure. So this figure, we have in x and y, we have plotted the contours of FF dual, and we start with FF dual to be 0 initially. At the center, we consider a Gaussian, and we see that it eventually evolves and spread in the space, as well as the value gets increased. So we see that gravitational waves can result in different effects and parametric resonance in non-abelian gauge field. So in overall, we have shown that thermal fluctuations lead to Z-N symmetry, and thermal fluctuation can also result in change in affect the KZM mechanism, as well as it can like mechanical fluctuation of like gravitational waves passing can also generate parametric resonance in non-abelian gauge fields. So thank you.